This lecture is about Neumann boundary condition. For the equation that we just started studying, for the equation negative u double prime is equal to f. So that is what we had before is u0 is a, u1 is b. This is called Dirichlet. This changed to maybe we give condition, as you may recall from ODE differential equation class. Another way is to specify u prime. Maybe u prime 0 is equal to a, and u prime 1 is equal to b. So in other words, if we have u double prime to f, and u prime 0 is a, u prime 1 is b. So anything wrong with that? One observation you might have is that u prime, u never appears u as a function. It only appears only u prime or u double prime appear. So if we define that u prime is equal to v, right? So we get negative v prime is equal to f, and v0 is a, v1 is b. Okay, v1 is b. On the other hand, we know that v1 is v0 plus the integral from 0 to 1 of v prime x dx. Okay, so if you tell me that v prime, negative v prime is f, we should have v1 is equal to v0 minus the integral from 0 to 1 of f of x dx, i.e. b minus a must be equal to negative 0 to 1 of f of x dx. This means that the boundary BDRY for boundary condition, if you want to specify boundary condition this way, boundary condition must be consistent, or it must be consistent. So the condition on A and B, you cannot give arbitrary A and arbitrary B. If you want to specify u prime at both ends, they must satisfy this condition with f. And in this case, when they are consistent, when the boundary condition is consistent, there is a solution for v. Basically, just integrate f, integrate negative f. You get a constant c, and you use the condition v0 is equal to a to solve for that constant. All right, that's typical ODE technique. Once you have v, you solve, then solve u from what we assumed, u prime to the v, right? So what does that mean? This means that infinitely many solutions. Infinitely many solutions for U. Alright, for U. Going back to the original observation, because U never appears, just U only appears as in U prime, U double prime. That means if you get a solution U star, then you can add any constant to U star. Alright, which is still a solution. Okay, so if negative U star, negative U lower star, double prime is equal to F, and U star prime 0 is A, U star prime 1 is B, then U is equal to U star plus any constant is still a solution, because once we differentiate, the constant goes away, right? So that means if you number this equation 1, the solution, so equation 1 is a 0 solution. Alright, when this condition is not consistent, or infinitely many solution. When the boundary condition is consistent, then there are infinitely many solutions. So that's not a very interesting case to study. We want to study the case when there is exactly one solution, right? There is indeed a high dimension version of this that I want to bring to your attention. So the higher dimension which is easily from a equality from calculus, from multivariate calculus. So in high dimension, that is, remember we explained first class, that's going to be negative Laplacian U is equal to F, alright? And given you know, the Neumann, the 1D is U prime, at 0 is 1, U prime is 1 is B. In 2D or 3D here is du dn, right? The normal derivative into G. In this case, if you have 2D case, you have 2D domain. Okay, so here is your omega. The n is this normal direction. Okay, so du dn is simply gradient u dot n, this direction n. Okay, that's a high dimensional version of u prime. What we have is a so-called divergence theorem. Divergence theorem from multivariate calculus. What that means is that if you have a vector field f, divergence of f, right, you integrate that in omega dx, that's the same as you integrate f dot n ds on the boundary of omega. Okay. And recall that the Laplacian is divergence of the gradient. All right, divergence of the gradient, which means what we have for the 2D or 3D is that that's divergence of the gradient of u is equal to f, and then du dn is equal to g. So if you define the vector field f above in the divergence theorem, the vector field is equal to the gradient of u, right? And apply that, and then apply the divergence theorem, and apply divergence theorem. So what we get is that divergence f we know is negative f. Okay, so we have we integrate on the boundary of negative f dx, which is basically the divergence of f, right? On the boundary dx, I mean not on the boundary, inside omega. If we integrate negative f, because the equation basically says that if we define f is equal to greater than u, is divergence of f, negative divergence of f is equal to lambda f, okay? Which means divergence of f is equal to negative f. So if we integrate that by the divergence theorem, we know that's equal to f dot n ds on the boundary, right, at the boundary. And well, what is that? What is f? We know that's greater than u dot n ds on the boundary, and which we know is du dm by definition. Okay, as we just explained. And what's this? That's we know that's given as g, right? So on the boundary of the boundary condition, g x ds which means that the integral, if you give me that condition, okay, which is the 2D version of the equation 1, the same equation 1, the 2D version, then we have negative the integral of f of x dx. Okay, this must be equal to the integral on the boundary of the g, the boundary condition on g ds. So that would be the consistency requirement. Compatibility or compatibility condition. This is the same. This is basically the for 1D, right? We see. Let's derive this and show it's basically the same for 1D. So in 1D, well, the omega is 0, 1. Okay, the boundary of omega is a set of 2 points, 0, 1. So what we're essentially saying is that we integrate from 0 to 1 of that f of x dx. All right, this should be equal to the integral of the condition g ds, and the boundary of omega is just 2 points, 0, 1. Okay, 0, 1. That's That's gradient u dot n, remember? So we have u prime dot n, all right, from 0 to 1. And what is u prime dot n? Let's just add u prime 1, okay? And u prime 1 for the 1D from 0 to 1. And we have at point 1, it's as a normal direction is this way, pointing outside of the domain. At the 0, the normal direction is this way. So this n, also this n. Okay, and this n is 1, that n is negative 1. So it's u prime 1 times 1 plus u prime 0, u prime 0 plus u prime 0 times negative 1, which is b minus a, okay? So the exact thing, means that b minus a is equal to negative from 0 to 1 of f of x dx. Same condition we derived before. Okay. So the type of less trivial Neumann boundary condition is a type of equation 2, which is we have net u double prime is equal to f, and we are given that, for example, u prime 0 is a, and that u prime at 1, we don't give u prime. Instead, we specify u1 is equal to b. Okay, u1 is equal to b. So again, we divide this into x0, xm plus 1 is x1, is xm. All right. So instead of before, if you put a Dirichlet at both ends, we're solving. Remember, we're solving just x1 to xm. Instead of that, now we solve x, because we don't know the value at x0, right? So we solve one more unknown. So one more unknown. So one more unknown, which means that we need one more equation, right? Equation, one more condition. What we had before is that we have two ui, right? Minus ui minus 1 minus ui plus 1, okay? Divided by h squared is equal to f at xi, right? That's what we did last time in last lecture. And here I is from 1, 2, all the way to m, all right? So so here is m plus 1 unknowns. These are m equations. All right, and we need one more equation. Basically, as we can see, is that we had never used the u prime 0 equals to a, the condition. All right. One way, as you might imagine, is that we do all the time for the find the difference is replace the derivative by divided difference. So u prime 0 is u prime at x0. That's maybe that is u prime u1 minus u0 divided by h. That's an approximation to u prime at 0, right? At x0. So that's equal to a. So that's one more equation, okay? And if we write the the corresponding matrix vector equation, we're going to get before, remember before, what we had is we have u1 to um, all right, u1 to um, and here we have 2, negative 1, negative 1, negative 1, negative 1. All right, this is equal to that f at x1, but we need to add that h squared u0, which is a, and then f of x2, f of x m minus 1, here of f x m plus h squared b. Okay, this now becomes the new system for this Neumann boundary condition. Well, instead of u0, from u1 to um, we're going to get u0, u1, um minus 1, and then um. Okay, and what we have is that the first row should give you this equation. This equation should become your first row. So which means, again, we have this 1 over h squared outside. 1 over h squared outside, okay? So that means you have negative h and h, because you have that h squared 1 over h squared outside. This is equal to, okay, this is equal to a. Why? Because you're going to get negative h times u0 plus h times u1 divided by h squared. That's just h u1 minus u0, right? That's equal to a. That's a enforcement of your boundary condition. Now remember, this first column now would hit u0. So from the second row, we actually have 2, negative 1, negative 1 there, right? And all the way to the end, we're going to get 2, negative 1, negative 1. Okay. Essentially, we take, so here is basically, the next guy is negative 1 here, alright? So essentially what we have is that we take the matrix from last lecture, and then we added a row, added a column, okay? Added a row, added a column. And the right hand side is nothing but now here, starting from the second row, we're going to get that f, right? F x1. This time we don't need to add that a over h squared, because we have the u0 on the left hand side is unknown, all the way to f x m minus 1. Now for x x m, this is the condition at xm. Now we do need to add that h squared u at xm plus 1, which is b. Alright? So that will be the way to enforce the Neumann boundary condition at one node. So we can do the next step, as we did last time, is to look into the local triangular error. Okay, the local triangular error. So we did the calculation of the tau. Okay, the tau. So now we're going to get tau 0, tau 1 to tau m, and tau 1, tau m, these are the same as last time, okay, the same as before. What about tau 0? As before, recall that what we had is order h squared, okay, from last lecture. What is tau 0? Tau 0 again is that how do we calculate the local translation error? Is we plug in the exact solution, okay? We plug and then we minus, we take the residual, right? And which is if you have h, you have u is the exact solution of x1 minus u at x0, okay? And minus the right hand side is the residual minus a, okay? And that's easy to see, and this is we do the same Taylor expansion. So here is u is x0 plus h, right, minus u x0. Let's take one more step, minus a. This is just h. You have u x0 plus u prime at x0 times h plus u double prime over 2 times h squared, and so on and so forth. This minus a, what is a? A is u prime, by the equation is u prime at x0, okay? And this will subtract u at x0. Okay, this is the same guy from here. So, and we see that this u0 cancel with the u0, and we have what's left is that u prime at x0 divided times h divided by h goes away, plus h over 2, right? H squared over 2 divided by h is h over 2, u double prime at x0, and this minus u prime at x0, and what we have left is order h squared. So we see that this cancels with that, but we have h over 2 times u double prime left, right, plus a higher order term, h squared. So this whole thing is order h. And if you recall, at tau 1 is order h squared, at tau 0, but tau 0 is order h. Okay, order h. This lack of accuracy at x0, comparing with x1, x2, all the way to xm, while the method has order h squared local translation error, the only location it has worse local translation error is at x0. That likely means that the method likely order h, the whole tau, okay. What this means is that the one way to fix that, we make tau 0 order h squared, right? The same as tau 1, tau 2 to tau m. Okay, but how? Okay, how? There are two kinds of technique. One is that you can replace. Right now we use the order h. Is basically the d plus, right? We use the order h, replace the order h divided difference u1 minus u0 divided by h by a higher order divided difference divided for example, the scheme that we derived is a 3u0 minus 4u1 plus u2 divided by 2h is equal to a. Okay, so we put 3 points there, and I'm not going to write down the linear algebra system. It's that's your practice. The second approach is that if you look at tau zero, if you look at tau zero, well, we just showed that tau zero is h over 2 u double prime and then x0 plus something order h squared, right? So basically, if we can get rid of this guy, then that's great. That's great. Because the rest is order h squared, the same as tau 1, tau 2, and so on and so forth. If you take a closer look at this, u double prime, we know u double prime, alright? So u double prime is negative f. So that's minus h over 2 f at x0. Okay? Plus order h squared. So the observation is that, well, tau 0 plus h over 2 f of x0 is indeed order h squared. Order h squared. This means that we can replace, if we replace u1 minus u0 divided by h by this is equal to a by u1 minus u0 divided by h is equal to a minus h over 2 f0. Okay, f0. Then we're done. Because the old tau 0 is simply, as we just did, u at x1 minus u at x0 divided by h minus a, right? The new tau 0 is u of x1 minus u of x0 divided by h minus a, minus the right hand side, which is minus a minus h over 2 f at x0, right? So this is just the u at x1 minus u of x0 divided by h minus a plus h over 2 f x0, which is old tau 0, okay? Old tau 0 plus h over 2 f x0. If you take a look, we get exactly what we just analyzed. That's tau 0 plus that h over 2. By this little trick, we made the new tau 0 order h squared. This is consistent at tau 1, tau 2, and so forth. So the scheme, by either the approach 1 and approach 2, the scheme would be order h squared.